Hi, in this tutorial we have an exercise related to stereoisomerisms. The question in the exercise asks us, identify the relationship in each of the following pairs of molecules as enantiomer, diastereomer, constitutional isomer, or unrelated. Assign R or S, cis or trans, or E or Z if the pairs are stereoisomers of each other. Let's start from the first one. The first one has two molecules, and if we analyze the structure, we have four groups bonded to carbon and four groups bonded to this carbon. And if you look at the groups, we have four different groups and four different groups, and the groups are same in both molecules, so they can be stereoisomer. And let's check whether they are stereoisomer or not. This molecule is a chiral molecule. The other molecule is a chiral molecule, so they can be mirror image of each other, or they can be enantiomer of each other. So how are we going to decide? There are two ways. The first one is you need to assign R or S to the first one and to the second one. If one is R and the other one is S, so they will be enantiomers of each other. If same, we are going to say that they are same molecules but drawn with different way. Okay, so the second way, we can compare the groups and how they look in 3D, and we can decide. For example, if we start from this one, the only difference between these two molecules, the location of methyl group at the back and the bromine on the plane, on the paper or screen plane, they are switched. And we know that if two groups switch in a molecule, we obtain the mirror image or the enantiomer. So if this is R, this has to be S, or if this is S, this has to be R. So that's the easier way. If you look at here, hydrogen and ethyl groups are exactly same in both molecules, only methyl and bromine groups are switched. So we will definitely say that these are enantiomers of each other. So let's write, so enantiomers of each other. Okay, the second task, we have to assign R or S to both molecules. If we just assign to one, the other one should be the opposite. So let's number based on Hahn-Ingold-Preluk sequence rule, the priority. We know that hydrogen should be ranked as number 4, and if I check the other groups, I have carbon, carbon, bromine. Bromine should be having highest priority. The ethyl should be having second highest priority, and the methyl should be the third one. And if we go through from 1 to 3, which way we are moving from 1 to 2, 2 to 3, the movement is clockwise. Normally, we have to say this is R, provided that hydrogen is going backward or dashed, but it is the opposite, wedged, so it's going to be the opposite. So this configuration should be S. If this configuration is S, the other configuration should be R. You can test yourself again by numbering from 1 to 4, and 4 should be at the back original, but here it's the same. So if you end up with clockwise, it's going to be S. If you get counterclockwise, it should be R. But as I said, since we decided these are enantiomers of each other, the first one ended up being S, and the second one should be our configuration. Let's move to the second one. The second one is not wedge dash style drawing. It is a Fisher projection. Fisher projection. And what is Fisher projection? Basically, instead of using dash and wedge, we just use straight bones, but the ones on the right and left sides are uh, wedged drawing, and the ones at the top and the bottom one should be a dashed one. Let's draw again like how they are. Basically, I'm moving them here. I'm going to just draw the first one. The first one is going to be like this. Normally, it should be like this, but in the Fisher projection, everything is just this one should be dashed, the other one should be dashed. So this is OH, and this is H. This is CH2OH, and this is also CH2OH. This is the translation of Fisher projection into dash and wedge drawing. But before trying to explain are these like R or S or stereoisomers, let's check whether the molecules are chiral or not. Okay, so I have an sp3 carbon here, and it has hydrogen OH, CH2OH, and CH2OH. It's the same actually on the other side. So I don't have 4 different groups. I have 3 different groups. I have hydrogen OH, and this group and that group are same. So this molecule is not a chiral molecule. So what's the relationship between these two molecules? They are same molecules actually. It looks like they are mirror image of each other, but since we don't have a chirality center, so these two molecules are same molecules. Basically, if you flip this molecule to the other side, or 180 degree from bottom to top or from left to right, you will end up with the same molecule. They are superimposable, so they are same molecules. Okay, let's move to the option C. In option C, we can see that there is a chiral center here, and there's a chiral center here, and we have 4 different groups. There's a hidden hydrogen here, and it should be dashed style. Here it should be a wedge style. There's a hydrogen here, and based on the structures, this looks like R or S, and this looks like the opposite. So they look like mirror image of each other. Why? Because I have again 4 same groups in both molecules, and all here this fragment and this fragment are on the same places on both molecules. They are drawn as straight bonds, and we just flip hydrogen with OH in the other molecule, so meaning that they are stereoisomers of each other, or they are enantiomers of each other. So that's the thing. So then let's decide which one is R, which one is S, after deciding that we have chiral centers and just 2 groups flipped in both molecules, meaning that they should be enantiomers of each other. Let's write here they are enantiomers of each other. And here I'm going to just use a dashed hydrogen. You can also place both this way depending on how you cite the molecule, and I will place the priorities. Oxygen should be number 1, and hydrogen group should be number 4. Here I have a methyl, and here I have a carbon with a double bond and a longer fragment. Definitely this part should be number 2, and this part should be number 3. And if we move from 1 to 2, 2 to 3, the rotation is clockwise, and if I check the hydrogen, hydrogen is facing away from the screen plane or paper plane. So yes, if it is clockwise, it has to be R isomer, and the other one should be S stereoisomer. Let's move to the option D, and let's analyze what is the relationship between these two molecules. This is an alkene and alcohol. So let's check. Basically, we have a double bond here. I will just number the double bond as like this. So let's say this is first carbon of double bond, this is second, and this is third, this is fourth, fifth. So I'm just numbering the ring here, and I will do the same. So this has to be 1, 2, 3, 4, 5. As you can see, the location of this OH and the location of that OH, they are on different carbons. So basically these two molecules are not stereoisomers, but they are constitutional isomers. That's right here. So the connectivity is different. They are constitutional isomers. Okay, let's move to last option, and let's check here. They look like stereoisomers, but let's see. Here in the first molecule, I have a chiral center. I have methyl hydrogen, this fragment and the other fragment of the ring, which are like we have 4 different groups. The same here, and in this molecule the same applies for this chiral center and that chiral center. But if you analyze each molecule separately, we can easily identify here a symmetry plane cutting the molecule into 2 equal halves. And also it's the same here. We have a symmetry plane in the molecule. It cuts the molecule into 2 like equal mirror image parts. So what does it mean? It means that these molecules, this is a meso molecule. If you have a plane of symmetry, even though we have chiral centers, the molecules are said to be meso. And let's say that this has R and this has S configuration. We don't know like whether they are R or S, but I just assign it should be the opposite here. This should be S and this should be R. They look like the mirror image of each other, but mesomolecules mirror images are identical to each other. So since the molecule is not chiral, it has a symmetry plane, a plane of symmetry, and its mirror image, it's not enantiomers of itself, but it's identical. So we have to say that these molecules are identical. Thank you so much for watching the video.